This is Dr. Anthony Revis with Introductory Concepts in Polymer Chemistry by Dr. Anthony Revis, Chapter 7, Polymer Performance. Let's start with a review of what the concept of rayology is, because in this chapter we will talk a lot about how to understand rayological properties of the polymers in order to determine or at least assess where they might be used in a final product. So, rayology deals with the deformation and flow of both solid and liquid materials. So it deals with the flow of the material and how that material deforms, okay, under stress or under some form of pressure. It studies the flow of liquids, soft solids, and solids with plastic flow, rather than basically deforming elastics under applied force. Let me repeat that. It studies the flow of liquids, soft solids, and solids with plastic flow, rather than deforming elastically under applied force. So rather than responding elastically on applied force, it looks at the flow of these materials. Okay? Mechanical behavior is an expression of the rayology of the materials modeled as a continuous mass rather than as a discrete particle. In other words, instead of looking at it as a discrete particle, it looks at the total mass. What happens to this mass of polymer, not a discrete particle of the polymer. The mechanical behavior is characterized by the flow of materials that exhibit combined elastic, viscous, and plastic behavior. You'll often hear the term viscoelastic behavior. It means that what it performs based upon its viscous or viscosity properties as well as its plastic behavior. You'll learn a little bit more about what those behaviors look like in this chapter and how they are assessed. And then when it comes to rayology, there's the concept of stress. Stress, which is a force per area, so it's a force across the area, causes fluids to flow. So we talk about fluids, but keep in mind here, we're not just talking about fluids as you think about water flowing, but these are basically viscous flows or for polymers. Rayology associates applied external forces and torque with internal stress and strain gradients and flow of the viscosity. So in other words, how does this polymer experience stress and strain when force is applied? What happens to the viscosity or this viscous material under stress? So we're going to look at that as well. Right now we're just trying to familiarize you with some of the concepts and with some of the definitions and terms. And the terms will make more sense as we go through it. The other concept that you'll think about is how do you practically use these materials? In other words, when you think about these polymers and these plastics, and you will hear me using the word plastics more and more, when you look at these polymers, these rubbers, these plastics, how do we think about them and how do we use them? Well, rubbers, plastic, and fibers, and other such polymeric materials are characterized using these rayological techniques, understanding how it deforms, how it flows. What are the mechanical properties? What happens when you stretch it and you bend it? When there's torque against this polymer, what's the stress? What's the strain? What's the viscosity? So, when we think about these rubbers, plastics, and other materials, we think about how they're characterized using these rayological techniques. And these are practical tools to examine how the polymer might perform in commercial applications, given the thermodynamic considerations that we've already discovered and discussed, and the polymer's physical properties. So thermodynamics of the polymer come into play because we know that the thermodynamics favors making the polymer, so the polymer will really like to stay put together, we prefer not to revert to monomer. So we understand that. And then we understand these physical properties. We understand that branching changes the physical properties. We understand that less branching gives a higher density because we have better packing of the polymer chains, and we know that more branching leads to lighter density, lower density, because the branches interfere with intimate contact. And so when we think about all of these and we put it together, what are the practical applications of this stress and strain, this torque, this twist, this bend, this mechanical operation of this polymer? That is what we look at in terms of rayology when we think about polymer performance. Okay, so it kind of brings it all together under this field. And you can check any good scientific dictionary or polymer dictionary will give you a really formal definition of rayology. But what I really want you to understand about it in the concept of this course is, how do we use these features to determine whether or not we have a plastic or material that might have commercial value? That's what we think about, okay, or some use, okay? That's how we're going to think about rayology. That's how we're going to think about its mechanical behavior. That's how we're going to think about the stress, okay? What practical value does it have in making these measurements, and how do we make these measurements, and how do we make these determinations? That is what you're going to hear, hopefully coming through in this particular chapter. So let's start with one of the mechanical tools or mechanical ways that these polymers are assessed. One of the things that's assessed is what's called as tensile strength. And what's tensile strength? Tensile strength is the stress needed to break the polymer sample. Okay, so what stress does it take to break the polymer sample? That it is that straightforward. That's what we're looking for, and that's called the tensile strength. Okay. Where does it break, and how much stress is required to break? Now it's expressed as pascals, or actually megapascals, and we show you the units for it. 1 megapascal is 145 psi, and a megapascal is the same thing as a Newton per millimeter square. Okay, so when we think about this, we think about pressure. And as we talk about this, you're going to hear in this chapters talk about PSI and megapascals, simply to help familiarize you with it using terms that you hear in everyday life. More people hear PSI than they hear megapascals, so I have them both here. But keep in mind, we use megapascals and actually newtons per millimeter square as the SI units. Okay, so tensile strength is an important property, especially for polymers that might be stretched. And because it's important for polymers that might be stretched, there's a tendency to actually take most polymers that are made and get the tensile strength, because it's a good comparison to other polymers. It's just a really good common comparison. You want to know how these polymers compare? Well, take a tensile and it'll tell you how they compare. And because of the history of understanding that property, many polymer scientists and non-polymer scientists for that matter can make some judgment about where this material might have utility. Okay? Fibers, for instance, must have good tensile strength. If you're going to have a fiber, you want something that's going to be stressed. It's going to be stressed, and it's going to be hanging. Things are going to be hanging off of it. Things are going to be pulling against it. It's going to find, it's a rope, it's a cable. You get it? That kind of thought process. So it's going to be pulled and tugged, and so it has to have good tensile strength. Okay, now let me give you an idea of what tensile strength looks like. Then we'll talk about how it's assessed. I show you a table just to give you an idea, so you can start to wrap your mind around thinking about tensile and PSI and pressure and how much pressure this really is. For example, to break a knee. No one wants to break your knee, of course, but it's just an example that kind of helps to get it in your mind how much pressure it is. It takes about 30 psi to break a knee. Okay, so if your knee experiences about 30 psi, it will break. And so if you convert that to megapascals, that's about 0.2. A nail gun at 90 psi, which is where you want to really drive your nail gun. And if you're not a carpenter, you won't get this. But for people that, if you've seen a nail gun, and you've seen at least the commercials and the television shows that had them in them. And that's about 0.6 megapascals. A propane tank is filled to about 150 psi, which is about 1. And a karate kick, which is kind of something to think about, has about 750 psi. In fact, some can go up to as much as 1,000. And the same thing with these martial arts and these kicks and these boxers and things. They can give you a really good punch there. But in terms of megapascals, that's about 5.2. A car gets crushed under about 16 megapascals, and atmospheric pressure, by the way, is 0.1. So that just gives you a reference point. So you're sitting around right now, you're experiencing 0.1 megapascals of pressure on your body. That's just what atmospheric pressure does. Now, some of these examples we're using here won't be directly comparable to the polymers, but it gives you an indication of the amount of force or pressure against this. So that was intent. That's the intent of that chart, and we'll use it from time to time just to kind of give us a reference point to sink our minds into just how much stress is being put on some of these polymers to test for the application, with good reason. Okay. For example, you want your seatbelt to hold, right? So there's a certain amount of stress that has to do. You want your hair tie to stay up. So a certain amount of pressure against it, if you will. You need to have an idea of whether it's going to meet those pressure requirements. All right. So when we do this and examine tensile strength, what we develop is a stress-strain curve, and we show the stress on the y-axis, the vertical axis, and we show the strain on the x-axis, the horizontal axis. And what happens is that this polymer is stressed and strained, and it creates a curve. So it's like pulling it against these two directions. So we pull it in these two directions, the stress versus the strain. And so the tensile strength then is the measure of that height away from the horizontal. So that's what we get. Where does it break? It breaks there, and that gives you a measure of the tensile, and that value is reported. Okay, so it's put in the instrument. That you'll learn the instrument in Instron or again, a device for measuring tensile, for stressing and straining the polymer, and you get a value. Okay, so you get that value, essentially that height, if you will, from the horizontal, and the distance from the horizontal, and that is your break point is the tensile strength. So we measured that tensile strength in an instrument. It's called an Instron. It uses to apply force to it, and we just show you a diagram here. And these is classically, you have your Instron and you have your dog biscuit. So you have your Instron here, and you have the polymer cut in what's called dog biscuit, and you put it in between these two jaws, and the jaw basically rises or is moved up, and clamped between the grip, and the test specimen is measured. That's essentially what happens. So we show you the schematic here of one, and then we show you what one might look like, a model of one on the page here as well. So this is what the instrument looks like, and this is how we acquire these values. Now again, I show you some comparison values. These were not acquired on an Instron, obviously, but again, the chart is only for reference to give you an idea of what these stresses might look like. So this is the instrument that you would use to do that, and you clamp the dog biscuits between there, and you get the values. Okay. Now we will show you some commercial polymers here soon and the values of those. Okay. So that's how we look at the tensile strength. Okay. That measures really which we acquire from a stress strain curve, the vertical movement away from the horizontal on the graph. Okay, so we take a look at that, Now, let's talk then next about the elasticity. For elasticity, elasticity is the ability of a material to resist distortion on the force and return to its original size and shape when the force is removed. So it's a rubber band. Okay, does it pop back? That's how we look at elasticity. It's distorted, meaning it's stretched, and then its ability to return to that original form once you unstretch it. So when you stop stretching the rubber band, does it go back? Solid materials deform when sufficient force is applied. When you put enough force on it, solid materials will deform. Elastic materials return to the initial shape and size when these forces are removed. Now, for small distortion, most elastic materials display linear elasticity. That elasticity can be measured by a linear relationship between the stress and the strain. Okay, as we show you again on the stress strain curve. Okay, and that's known as basically as Hooke's law. Okay, which is an expression of tensile force and the corresponding displacement. So we have the tensile force and what the displacement of that is. Okay. Therefore, plot again of stress versus strain yields a value yields a valuable I'm going to say that again. Therefore, a plot of stress versus strain yields valuable information about the elasticity of the polymers. So in other words, when you look at the stress is the average restorative internal force over the area, and strain is the relative deformation. So you look at your stress versus strain, and then we develop that curve, we take a look at that curve, and it gives us some idea, okay, about the mechanical properties of that polymer. So how do we report these values of elasticity? Young's modulus measures the elasticity of the polymer. It's called Young's modulus. Okay, so if you hear the term Young's modulus, they're asking what's the elasticity of the polymer. Is defined as a ratio of the rate of change of stress to strain. Okay, so basically, yeah, it's the slope. So what's the slope? And it's also called the modulus of elasticity or the tensile modulus. So you have Young's modulus, which is the same as modulus of elasticity, which is also the tensile modulus. And we have to pick a point where where it makes sense to measure the slope. And for doing Young's modulus measurement of the slope, which is by far the industry standard, we measure it at the very small, where there's very small movement in the stress and strain curve. So you go back to the beginning of the stress strain curve, you take a look at the slope at that point before it starts to deviate, and that's where you draw the line. And that's a very consistent process. Now the apps, the computer will do all these kinds of calculations for you. It will acquire that data. You don't have to do it by hand, obviously. And that is a very consistent way of getting a number that gives you an idea about the elasticity of the polymer. And then you would take that elasticity and oftentimes you compare it against a standard. And, natural rubber, for example, it's really the original standard by which, elasticity might be compared or was compared. So you basically compare it against a standard or some other material to get an idea of where it fits in terms of its elastic profile against other polymers. Keep in mind, a lot of polymer chemistry is compared against standards and compared against itself. And the way you know a polymer is best for the application is it works. When it works for the application, that is the right polymer, and therefore you will retro-analyze many of these properties, and you will set those as your standards for performance for that application. So we have tensile, we have modulus, Young's modulus. We know about elasticity. Okay, one of the other properties we want to learn about is elongation to break. How far can I stretch the rubber band before it breaks? That's the question being answered here. The elongation to break is a strain on a sample when it breaks. What was the strain on a sample when it broke? This usually is expressed as a percent. So the percent of elongation is what you're really interested in. And rubber bands and things like that will go up to 1,000%, for example. The elongation of break sometimes is called the ultimate elongation. It just kind of makes sense. So you'll hear those terms used. Fibers have a low elongation to break, and elastomers have a high elongation to break. In other words, fibers are designed not to stretch. They do have an elongation, but it's very, very small. Elastomers, on the other hand, are designed to stretch, but some elastomers are designed to have have less stretch than others. Okay, so you want to keep that in mind. So here again, the elongation then would be the movement from the vertical line across the horizontal. Okay, so you move from left to right, if you will, or right to left, but actually left to right is how it's measured. And so we have the stress and the strain. So how much strain is put on this rubber band before it breaks? So if we take this rubber band or we take this polymer and we stress it and strain it, we can get this information. We can understand things about its elasticity and elongation. It's tensile. We can actually calculate these values. Okay, and again, the elongation is the movement across the from the vertical across the horizontal. Okay, and we examine how long the percent elongation until it breaks. Now, materials, we want to know the tensile, we want to know the elasticity, we want to know the elongation. One other thing we'd like to know is the toughness. How tough is this polymer? Okay? Toughness of a material is the area under the stress strain curve. That's it. How much area is under the curve is calculated mathematically, but the apps and the software now does this job. We acquire that area, and that's how tough it is. The stress is proportional to the tensile force on the material, and the strain is proportional to the length. So you have your stress versus your strain. The area on the curve is then proportional to the integration of the force over the distance the polymer stretches before it breaks. So basically, to determine the toughness, you would take the polymer to the break point. This integration is the work or the energy required to break the sample. And you understand work is energy. Okay? And energy does work. The toughness is a measure of the energy a sample can absorb before it breaks. So just how much stress and strain can this polymer take before it breaks is what you want to know. If it's an elastic latch of some type, how many bends or how often can I do this or how far can I stretch this before it will break? You'll want to know that when working with polymers. Okay? And again, the area on the curve is the toughness. Now, just to compare, I'll give you an idea. Your knee again can only take about 0.2 megapascals before it caves in. Okay? Now, a crushed car can take as many as 6 megapascals before it's crushed. These are not exact, certainly not the car. The crushed car is not really apples to apples. It might be apples to some other fruit comparison, but it gives you an idea of how tough polymers can be for their applications. Okay? And that's why these are on there. They're not perfect examples, but just to give an idea of what's of the relationship between these and some things that you might be more familiar with. is a difference between toughness and strength. And that is the differentiation we like to make. Okay? There's a difference between toughness and strength. A brittle material is strong but not tough and cannot deform very easy. You got it? So you can have a brittle material that's strong. It's very strong, brittle material, but it's not very tough. So you keep that in mind. You can have it, and it's brittle. Okay, it's brittle, and the brittle material, is strong, but the brittle material cannot deform very easily. And I think you intuitively understand that. Okay, so you want to be aware that toughness and strength don't mean the same thing. All right. For example, polystyrene is brittle. High impact polystyrene, called HIPS, which is a blend of polystyrene and polybutadiene rubber, is rubber toughened. Okay, so with rubber toughened, you get a different curve. And so we show you some examples of what these curves might look like, the stress-strain curve and the relationship of that stress-strain curve. So if we take a look at a material that's strong but not tough, it would go up really, really steep. Okay, a strong and tough would almost go right up. Okay, right up the middle. Okay, all right up to 45. One that's neither strong nor tough would be have a very low slope. Okay, so a very strong but tough, high slope. Strong and tough, okay, would have a slope right about the 45, and neither strong nor tough would have a very low slope. So if you take a look at the stress strain curve for polystyrene versus HIPS, you will see that HIP kind of goes strain right on that, kind of starts up and has a little bit of a hump there, and it goes out the horizontal. But polystyrene itself is very strong but not tough. Okay. HIP on the other hand, okay, is somewhere a little bit stronger, right? And has a little bit more toughness in it. Okay, and that's what you look for. And you look at the area, and so when you examine the area on the curve, you get a different area on the curve for HIPS than you do for polystyrene, and that's worth noting. Okay, all right. So again, polystyrene is brittle. Okay, high impact HIPS, okay, is rubbery and is rubber toughened. So you have a little bit of the rubber toughening there for that polymer. And when you look at the stress strain curves, it helps you to view that. Another mechanical aspect of polymers that we like to highlight and talk about is ductility. When we think about this particular mechanical property, ductility is the degree of plastic deformation before it fractures. How far does this plastic deform before it fractures? Okay, it's how much strain a material can hold before it fractures. So how far can we strain this polymer before it basically fractures, cracks, falls apart, breaks apart? Okay. Polymers are typically low in ductility and pliable, yet less stiff and strong. You get it? So polymers are typically low in ductility and pliable. Okay, they're low in ductility. Okay, and pliable, yet stiff and strong. Okay. So, we show you here some curves, stress versus strain curves of materials, and these curves will help you understand the types of properties that the plastic might have and which category it falls into. So let's just take a look at them and examine them. The first one curve here is A. The curve represents strong but not ductile. Okay, it stretches a little but fractures suddenly. So a little bit of stretch and then it snaps all of a sudden. Okay, and then we have brittle. Okay, barely deforms and fractures suddenly. And that's what happens if we have a B-type polymer. C polymer, on the other hand, is ductile. It's plastically deforms before it fractures. In other words, it will plastically deform before it fractures. It's a little bit like stretching a bag. And we talked earlier in an earlier chapter about necking. So basically, the polymer would stretch and deform before it fractures. It won't just suddenly pop and snap. Okay? And D, mostly plastic, fractures before the C. So it's mostly plastic, but it'll fracture before C. So C might be something, a plastic that you use or something. You know you're going to put something really heavy in, and you don't want it to pop on you all of a sudden, right? So you kind of put in, you want that bag to stretch a long ways before it pops. This type of curves used a lot for determining which bags are going to be made and used for what applications. So a lot of your plastic will undergo this to determine, is that plastic bag or plastic container going to be good for a particular application. This is also why you get frustrated when you get some bags and you put your stuff in, all of a sudden it just kind of pops through. Well, it's because its stress strain curve was such that it would not deform, or did not have plastic deformation, that is, before it fractures. So if you're going to take a plastic bag and put something in heavy and you want to make sure it gets there, make sure it has plastic deformation before it fractures. Okay? Now, to give you an idea of what types of polymers might fit this, and keep in mind this is at a pretty rudimentary level, but these are good examples for you to think about. For example, the A-type polymers, there would be ceramic polymers in that, so we're in that A-B kind of area. If you had ceramic polymers, which we're not really addressing in this introductory concepts course. Then you have the thermosets and thermoplastics, which start to be somewhere ranging around that slope area of the C-type polymers, and you also have polyethylene and PMMA that would be probably below the slope of the C-type curve, and then your elastomers would be somewhere around, probably actually a little lower than the slope of the D-type polymers. So this is giving an idea of of kind of where and what types of polymer might fall, generally speaking, into these categories. Again, this is not an ideally drawn diagram here. You could find more detail, but this gives you an idea of what the concepts to expect. So you expect the types of polymers that we're talking more about would be those thermosets and thermoplastic matrix, and matrix resin means that this is a compounded polymer. It's a polymer, and it has fillers and other materials added to it and other additives to make it into a final product. It'd be like maybe your tires, for example, on a vehicle. And then you'd have your bags, polyethylene bags and things of that nature, and PMMA types of materials would fall probably a little below that PMMA for certain types of PMMA. Then you have the elastomers that will fall down, less slope on the elastomers. So now that we've talked a little bit about these, let's just take a look to try to give you an idea of what types of materials fit within these. So we show you some tensile strengths here now of some common polymers, and we show you also the elongation and the Young's modulus. So in this first table that we show you a comparison using stainless steel balls, just to give you an idea as a reference point there. Then you look at cellophane film, has tensile of 500 to 120 there, compared to nitrile rubber, which you know the nitrile rubber sheets are you make the nitrile gloves from, is about 20 to 30 in terms of its tensile. And then fiberglass yarn has about 1400 PSI tensile. So that gives you a pretty good idea of how much tensile strength is in there. And not, again, a perfect apples to apples comparison. You note that, again, at the bottom we show you some examples of some pressures against some items that you're at least familiar with, car and your knee. So then we look at the percent elongation to break in these very small stainless steel, right? You might expect that. Cellophane's bit is much more. Then yarn, the fiberglass yarn, has pretty high tensile, but its elongation is not very much. It doesn't elongate much at all, as opposed to nitrile rubber, which is expected to elongate. Then you look at the Young's modulus here. For nitrile rubber is very low. Cellophane's 3. Then you have a high Young's modulus, as you might guess, for stainless steel. When you think of the Young modulus, it's basically the ratio, the rate of change of the stress to the strain. And so in the case of the stainless steel, you get these units when you integrate underneath the curve, you get 200 versus 3 for cellophane, and that's to be expected. And nitrile rubber is very, very low. Okay, again, and that too is to be expected. Fiberglass is 72 and 2. Okay, so that's one set of data. Now let's just take a look at some more with just all these well-known polymers, and we won't go through these, but you have these different polymers ranging from polyamide plus glass fiber would be at 150 versus if you take the glass fibers out, the tensile is less. And so those are things that we often do. You'll reinforce a polymer with some filler and glass fiber or some fibers, and you get it increase its tensile. You do the same thing if you look above on the table with the acetyl copolymer. When it's non-reinforced, you get tensile of 60. When it's reinforced, you get a tensile of 110. Likewise, the ABS polymer, which is used, the ABS polymer is used in Legos. You have the ABS polymer when it's glass fiber enforced, the tensile goes up. So that is one of the take-home principles that we learn about tensile and elongation and modulus, is that it can be modified depending on what type of additives we put in. And one take-home point from this is that when we add glass fibers, the tensile is increased. Okay, so we increase tensile by adding the glass fibers. Now, if we take a look and compare again that ABA polymer, notice in the unfilled system, which means just ABS with no glass fibers, we get a 30% elongation. But when we add the fibers, the elongation goes down. We note also that we see the same trend in terms of acetyl polymer. Elongation is decreased by adding the fibers to that as well. And we see the same thing in the polyamide. When we add the glass fibers, the polyamide goes down in terms of its elongation. So you start to get an idea of how these other properties are affected by that. Now, we can see some other trends when we look at the tensile modulus. Look at the tensile modulus of ABA, and I'm just comparing these so you can see the impact of adding fibers as well to this. If you add the fibers to the ABS, the tensile modulus, you might expect it, goes up. Also in the acetyl polymer, it goes up. Okay, in terms of its tensile modulus. And if we look at the imide, the same trend holds true for it. The tensile modulus goes up. I would expect that these are some trends that you want to memorize or you want to learn in terms of looking at a course like this. The impact of adding fibers on the mechanical properties. And this chart shows you some very good comparisons, okay? And the real bottom line is that the ultimate tensile and the tensile modulus increases with the filler, but the elongation decreases. So let's show you some example then of some polymers and how they perform. Let's start with this acetal copolymer that we've talked about already. In this particular case, we show you an example of what happens when we modify from what's called the polymer H to polymer C. Both systems are unfilled, and we show you what it looks like, the elastic modulus, how it's modified over the temperature range for this particular copolymer. It's a copolymer used to make threaded plastic devices for various applications. An example one is shown here in the slide. So we look at the temperature dependence of the unfilled acetal homopolymer and the copolymer. They follow the same trend, except there's less area under the curve of the unfilled system. So you have the homopolymer, more area under the curve. Therefore, it is a different polymer. It is a unique polymer, and for many of the applications, you might be able to use them interchangeably. But there may be applications where you cannot use them interchangeably. So this is what its elastic modulus profile will look like. And this is an example of how chemists might examine two different polymers. They would take a polymer, examine it, take another polymer, examine it, put the curves, take a look at the curves, look at what's required for the application, and make a decision. Now, we have more data to show you on this one. So let's take a look at the rest of the data before we reach our conclusions. So if we look at the mechanical properties of this acetal polymer, okay, we look at the property of the homopolymer and the copolymer, and we're going to also look at, okay, the filling it with glass to see the impact. So if we look at the tensile strength of the homopolymer, it's at 69. The homopolymer has higher tensile strength than the unfilled system at 61. Likewise, the homopolymer has higher tensile modulus than the filled system. Its tensile modulus, is a measure of its elasticity. So when we think about elasticity, right, of it, we get these values, okay, and then we take those same systems and we fill it. We fill those with 20% glass, and it's pretty interesting to note what happens when the homopolymer is filled with 20% glass. Its tensile strength is less than that of the copolymer. So you see, that's pretty interesting. That tells you there are interactions in the copolymer that are different, and the way it compounds in and mixes in is different. Keep in mind, you have these two, this is a mixture, and you're trying to mix this in a fashion. They're heterogeneous. They don't dissolve into each other. They basically mix with each other, and they interact, and the interaction for the copolymer with the 20% glass is different. Likewise, the tensile modulus for the homopolymer with 20% glass is less than that of the copolymer, and this is a pretty good example, a classical example of what can happen. And sometimes we think we can predict all the properties of what's going to happen, but you really have to carry out this study to make the material, get the measurements to make a determination. Polymer chemistry is a very practical field where the winner is the one that gives you the performance you want. And more times than not, polymer chemists will make the materials after they've gone through all the theoretical analyses to see what works, and that is what will be the final determining factor in whether or not this material might be accepted for that application. Let's take a look at another example of a polymer. Another example of a polymer or a copolymer is the ABS polymer. A very popular application for the ABS copolymer is the Lego blocks. And another one is the pocket jig tools that you use to make grooves in furniture. I'm familiar with them. Actually, I'll probably go buy one. But the point I want to make here is that it's a real popular tool for people that do woodwork. So if you do woodwork and you work with any of these tools, and many of the tools that you actually work with that look like that plastic on it, many of them use the ABS copolymer because it's such a tough polymer. And we show you the structure here. It's a combination of styrene, butadiene, and acrylonitrile. And so when we look at it, we find that it has an elongation of about 30%, tensile modulus of 2.3, and its ultimate tensile modulus is 40 megapascals. And again, we show you over on the left side just an example of some comparison, just by way of reference. Again, these are not good comparison apple to apple, but give you an idea of the amount of force that this plastic can take. And that's why it's actually used for these particular applications. For applications where the plastic is going to be thrown around and dropped around and chucked around a lot, ABS copolymer is used that way. And in fact, many of the leading manufacturers will make that as a point because people have intuitively become, that is, in the construction industry, they have intuitively become accustomed to certain polymers. Like if they're going to do caulking, they want to know if it's siliconized. If they're going to buy these types of tools, they want to know it's the ABS. Am I buying an ABS pocket jig? And many of the manufacturers will sell it calling it an ABS jig tool. Okay, for them because they're accustomed to what that means. So we have this polymer which shows these characteristics. So these are examples of polymers that show mechanical properties. We're going to switch gears slightly to introduce one final concept: polymer surface tension. And so we show you here the wetting of polymer surfaces, and that's what it amounts to. With water as a standard at about 73 dyne per centimeter. And what we like to show you and note here is that each of these has its own unique surface properties, and those surface properties help with how it interacts with other materials. If you want to use for wetting, or it's going to be water wet or what have you. Water being 73 means it's wets real well, and silicone does not wet. And so you also know the ABS doesn't wet, and the construction guys really like that because the water just beads up on it. They shake it off and they can keep right on. It doesn't soak into it. So all of these you look at, this is kind of one of the important factors about to understand about the surface property of untreated polymers and plastics. They don't wet. Okay. However, you can change them and treat those surfaces where they can wet. So, for example, a manufacturer wants the appeal of the polymer, wants the other properties of the polymer, but they want it to wet. They want it to take a little bit of water. They want water to wet it so it can be wiped down or washed down or what have you, or whatever the application is, or maybe it's going to move from construction to textile. Then they might treat that polymer surface in a way that allows it to be more wettable. So you notice here you can take these same polymers that are very hydrophobic. So it's 32. When you get into the 30, when you get down to the 30s, they're pretty hydrophobic. Okay, so you can take these hydrophobic polymers and make them more hydrophilic, more water-liking once you treat them. That is one of the uniquenesses of working with the plastics. You can modify the surfaces. You can take the other mechanical properties, develop them, and then you can modify the surface for further interaction. And that's an important feature for them, and it improves their acceptability in the marketplace. So let's talk about a couple of specialty polymers. One example of a specialty polymer. Then again, we are switching gears slightly here as well. But again, we've talked about these mechanical properties, and because of these properties, there are some polymers that have differentiated themselves or been distinguished because of their mechanical properties, their physical properties, and their rheological properties. So one of them is silicone or polysiloxanes. Silicones or polysiloxanes, that's the same thing, are polymers that contain repeating units of silicon and oxygen atoms in the chain. I need to point out that silicone is not the same as silica. Silica is in your cell phone and electronic devices. Silicone is around your bathtub and in your kitchen as appliances. There is no silica in your kitchen. If it was, it's a very expensive device. If it's there, it's in the electronics of your kitchen. So these are silicones. These are your bathtub caulks or your rubbery materials, not the hard metal in your cell phones or electronic devices. Silicones are formed by condensation polymerization. We talk about condensation polymerization. That means it eliminates water in the process of being formed. Silicones are typically heat resistant, and that is one of the key features that manufacturers love and like about silicones. They like the fact that the silicone is heat resistant. Okay? And even when it's a liquid or rubber-like, and that's why you can use them. Many of the silicones find good applications in kitchen appliances, baking, and things of that nature. They're used as sealants, adhesives, lubricants, used in medical applications, using breast implants, soft contacts. As we pointed out, cooking utensils. They're using heat transfer fluids, thermal electrical insulation. There are many applications for silicones. Silicone sealants are well known in bathtub caulks. We show you here in a reaction of how silicones are typically made from what's called a dichlorosilane. That dichlorosilane is hydrolyzed, and somewhere in between we get a diol that's not very stable, and it goes on to form the polysiloxane or the silicone. And we show you the repeat unit is going to be the dimethyl SiO for a dimethyl, and you will have these as linears and cyclists. The cyclist called dimethylcone, and you'll hear that term used when it refers to digel, for example. So this is what a silicone looks like, and we already noted it's very hydrophobic material. Its surface energy is only about 32 dyne per centimeter, which makes it water really bead up on it. A fun example of silicone is silly putty. It has very unusual properties that really interesting stress-strain curve relationship. Because it bounces, it will bounce, but will break when given a sharp blow. It can also flow like a liquid. So you can take silly putty, roll it up in your hand, and bounce it. You can take that same silly putty and with enough force throw it against a brick wall or solid wall, and you can shatter it. Or you can set that same silly putty on your desk and it'll start to ooze across the desk and lay out flat from the ball. So 3 unique properties features of properties in one basic silicone material. And you note also the silicone fluids can be used from very cold temperatures to very hot temperatures. This is why it's especially material that's found great application across many industries. Another special polymer that we like to point out here because of its unique surface properties, pressure sensitive adhesives. They are viscoelastic polymers with rayology tuned for bonding and debonding based on the pressure. So you can stick it on or you can stick it off. The Post-its, by the way, are another good example. You stick them on, stick them off. That is a PSA, a pressure sensitive adhesive. And you have the tape, Scotch tape. That's a pressure sensitive adhesive. Duct tape is questionable whether it's pressure sensitive for removing, right? It goes on but hard to come off. But really duct tape can come off too. So these are all pressure sensitive adhesives. They've been well tuned for applying and removing. The common polymers include acrylate, silicone, rubber, thermoplastic and thermoplastic elastomers. These are some of the common polymers that are used. Similar polymers are used in permanent sealants as well, except the difference is the formulation is changed to allow it to form permanent bonds once it seals, it cures to the surface, and those bonds are harder to remove. The surface tension of the PSAs, pressure sensitive adhesives, is tuned such that it does not form a permanent cure. However, if you've ever put a piece of tape on a material and left it there for a very long time, a year later you come back, it's dried out, that's because the viscoelastic material that's in there tends to continue to harden, and once it hardens, it doesn't come off as easily. The properties of PSAs, polymers, they're blended with what's called a tackifier. So you put it in a low molecular organic silicate, it makes it tacky, and that's for the grabbing power and deformability of it. You want to put a tackifier in the polymer blend. Okay, they're low surface energy, as we pointed out. Okay, and they accept many surfaces and are moisture resistant, and that's an important feature of a good PSA, is that it really doesn't care about the moisture. Yes, they stick better if there's no moisture around for some of them, but really the moisture doesn't overall stop you from being able to use a pressure sensitive adhesive. The polymers typically have low cross-linking density, and that's pretty important to how it flows out and doesn't harden out as fast. Low viscosity is another important feature of it. These are features you want to think about, and this is how if you want to prepare your own PSA. And a broad range of molecular weight distribution, and that's to control the adhesion and peel. In other words, what the polymer chemists will do is take a formulation and they will blend in other polymers, other additives to control how much pressure it takes to pull it off. That's what they did with duct tape. They modified it so that it would stick even more. And with the Post-its, that was modified less at 3M so it come off even quicker, but not fly off. You get it? And the other part they have to think about is how they, when they're manufacturing these, when they're on the line, will they fly off on the line? Which means the underliner that the tape is on has to be considered too. In the case of roll up tape, the backside is the liner. And that design has to be where it pulls away cleanly from it. But when you pull it away cleanly from the roll, it will stick to the paper. A lot of really cool chemistry that goes into this when we look at the mechanical properties and how they all come together. This is a great example of the of ingenuity in terms of pressure sensitive adhesives and matching mechanical and physical properties of polymers and other materials. So we talked about, and we mentioned that PSA backing. The release line of polymer allows for peel off of the adhesive, and these polymers are cured on a backing. In the case of tape, it's on the backing. One side is the adhesive, and the other side is so that it doesn't stick when you roll it up. Many of these PSAs are cured onto the backing by using UV and heat. Both techniques work. It depends on the manufacturer, their capabilities, their patents, or the particular application. Okay? One of the things important, however, is that they must match the toughness, flexibility, and environment for the application. That's what duct tape is really a good example. It matches most environments. Okay? But for Scotch tape, you just need to stick it on your paper. It's good to go. You don't need to be out in the weather or anything of that nature. It works. Similar with a Band-Aid. Okay? The Band-Aid has to be able to go on the human flesh, stick there, and be able to pull off easily. And you might note this is how they do the children Band-Aids. They will modify the PSA, the pressure sensitive adhesive, so the peel doesn't yank as much against the kid's skin. Now, this slide shows you a little bit more of what a formulation of a PSA might look like. So here we show you that blend when we talk about the various polymers. You may have, we show you the ethyl hexyl acetate, methyl acrylate, butyl acrylate, lots of acrylates in there. These cure into the system, acrylic acids there, other methacrylates, vinyl compounds, and you have the initiator, depending on which initiator you want to use. In this case, we show you an example of Vaso 67, which is initiator. And then we have the solvent. And so you make this blended material and then you cure it out. You notice it's very low solvent blend of material, and that's kind of good because it helps the environment. So you make these, it has the wet. We show you what non-wetting looks like in the top diagram. The angle there is greater than 90 degrees. So when it's greater than 90 degrees, it won't wet. When it's less than 90 degrees, it will wet. And so that's what this is intended to show here. So liquid is non-wetting. Okay, when the surface tension is dominating the attractive forces on the surface. But then when the attractive forces to the surface exceed the surface tension, the liquid wets the surface. That means it's greater than 90 degrees for the angle. Okay, so again, non-wetting is less than 90 degrees on the surface. Wetting is greater than 90, and these two factors have to be matched when you're making PSAs. And depending on the application of the PSA, will help determine just where you want that to be. And these blended materials is what gives you that final property performance. And one other specialty polymer that we like to mention is one that has green raw materials. It's polylactic acid, PLA. It's called a common renewable polymer. It is part of the green effort to make polymers more environmentally friendly, as in more biodegradable. It comes from nature, go back to nature. Okay, so PLA is a thermoelastic polyester. So it's a polyester, and it's polyester that's made by condensation of the corresponding acid. Okay, by biting basically its own tail. It's head to tail polymerization here as a condensation, which has a similar look or feel as PET. So your PET has a similar feel and similar application, and it's prepared again by condensation. The PLA softens at 146 degrees C. Okay, as compared to PET at greater than 250 degrees C. So it has a lower softening point, but can be used for many of the same applications. It includes clear, shiny bottles, transparent food packaging, these beautiful looking food packaging, clothing fibers, plasticware, your plastic spoons and forks, and coatings on paper cups and plates to make them water resistant. And again, this would be preferred over PET, all other things being equal, in other words, the availability of the raw material. Manufacturing is a cost that can bear it, and the consumer can bear buying it. So if things work out, then you replace something like a PET, which is not does not come from a renewable resource. Okay, which means it has to be recycled or landfill or worked into new products. PLA, on the other hand, is designed to fit the biodegradable family of new products that industry is really seeking to move with. So its monomer is lactic acid, and it contains a carboxylic acid and a hydroxyl functional group that bites its tail and gives you the polymer. So there you have it. That completes Chapter 7, Introductory Concepts in Polymer Chemistry by Dr. Anthony Revis.